Evaluate the triple integral over d of the natural exponential raised to the square root of x squared plus y squared plus z squared, where d is the solid region bounded by y is equal to the square root of 4 minus x squared minus z squared. So we want to consider our bounding region here first. So we want to consider d in R3. And all we're given is that it's bounded by the surface y is equal to 4 minus x squared minus z squared. And so we recognize that this is a hemisphere centered at the origin with a radius of 2. So because we have a radius of 2 and we're centered at the origin, we can say that the bounds on rho, which is the radius of our sphere, are from 0 to 2. But we also need to think about the bounds for phi and theta. So we want to consider the two-dimensional region R and R2. So here, instead of being in the xy plane, we're going to consider what this projection looks like in the xz plane. So if it's in the xz plane, we're going to let y be equal to 0. And we can make a little note here to ourselves that since the solid region D in R3 is a hemisphere, this tells us that the projection into R2 will be a semicircle. And so, therefore, the bounds on theta are from 0 to pi, and the bounds on phi are from 0 to pi as well. And so the last thing that we need to do here before we can begin integrating is to rewrite the function, or the integrand. And so we were given f of x, y, z is defined as the natural exponential raised to the square root of x squared plus y squared plus z squared. And we again recall, since rho squared is defined as x squared plus y squared plus z squared, we can substitute that into the radicand of the square root. So we can say that our function in terms of rho, theta, and phi is now the natural exponential raised to the square root of rho squared, which simplifies to the natural exponential raised to the rho. So we have our bounds on rho, we have the bounds on theta and phi, and we have our function in terms of spherical coordinates. So we're ready to start integrating. So let's set up this triple integral and evaluate. So again, we were given the general triple integral over d of the natural exponential raised to the square root of x squared plus y squared plus z squared dv. And we have converted this to the integral. So keeping my theta bounds on the outside, that's 0 to pi. The middle integral is phi, which is also 0 to pi. And the inner integral was rho, which was 0 to 2. Then I have the natural exponential raised to the rho. And then don't forget that we have the differential rho squared times sine of phi, d rho, d phi, d theta. And so notice here with this triple integral, we have constant bounds. So I'm actually going to go right ahead and split this up into 3 separate integrals. So my outer bound are with respect to theta, and the integrand doesn't contain any theta, so our first integral here is just from 0 to pi d theta. And our next integral is with respect to phi. So we want to include sine with this. So we have, this is multiplied by the integral from 0 to pi of sine of phi d phi. And then last but not least, we have the inner integral, which is with respect to rho. So grouping all those terms together, we have the integral from 0 to 2 of the natural exponential raised to the rho times rho squared d rho. And we're ready to start evaluating. So our first integral with respect to theta, I have 0 to pi d theta. So this integrates to theta from 0 to pi, and we are left with a beautiful final answer of pi. Next, we are integrating with respect to phi. So I have the integral from 0 to pi of sine of phi d phi, which integrates to minus cosine of phi, which we're evaluating from 0 to pi. So I have minus, I'll keep the negative on the outside, I have minus cosine of pi minus cosine of 0. So no, cosine of pi goes to -1, cosine of 0 goes to 1. So we have minus a minus 2, which leaves us with a beautiful final answer of positive 2. And then last but not least, we saved the most exciting one for last. We have rho, which is from 0 to 2 times the natural exponential raised to the rho times rho squared d rho. And so in order to integrate this, we're going to need to use integration by parts. And so I'm going to use my acronym here to decide what U will be. So I think about that acronym ILATE. So when we look at our integrand here, we think, are there any inverse trig functions? Nope. What about logarithms? Nope. Algebraic expressions? Yes. So this tells us that we are going to let U be rho squared, and then whatever's left over is our dv. So that's going to be the natural exponential raised to the rho d rho. And so from u, we differentiate to get du, which is 2 rho d rho. And then from dv, we integrate to attain that v is equal to the natural exponential raised to the rho. And so plugging this in, we have u times v, which will evaluate from 0 to 2, minus the integral from 0 to 2 of v du. So we have the natural exponential raised to the rho times 2 rho d rho. So we're going to need to use integration by parts a second time here. So we'll give ourselves a little bit more room. So again, we can see we have this algebraic expression for parts. So in this case, I'm going to let u be 2 rho, and we let dv be whatever is left over, which is the natural exponential raised to the rho d rho. So then from u, we differentiate to get du is equal to 2 d rho, and from dv, we integrate to attain v is equal to the natural exponential raised to the rho. And plugging these back in, we have rho squared times the natural exponential raised to the rho from 0 to 2 minus, and I'm using brackets here for my safety, so then we apply parts, so I have u times v, which is 2 rho times the natural exponential raised to the rho from 0 to 2 minus the integral from 0 to 2 of v du, so that's going to leave us with 2 times the natural exponential raised to the rho d rho. And we're excited here. We can see that this is a general antiderivative, so we'll be able to integrate. Just be mindful of your signs. So this is equal to, we still have rho squared times the natural exponential raised to the rho minus 2 rho times the natural exponential raised to the rho plus 2 times the natural exponential raised to the rho. And we're now going to evaluate this whole expression from 0 to 2. So plugging in 2, we have 4 times the natural exponential squared minus 4 times the natural exponential squared plus 2 times the natural exponential squared, or excuse me, that's should be a square. And then we are subtracting, plugging in 0. So the first two terms disappear. We have 0 minus 0 plus 2 times the natural exponential raised to the 0, which we know goes to 1. So looking at the first term, those will cancel each other out to 0. And we are left here with 2 times the natural exponential squared minus 2. And we can even factor out a 2 here. So this is 2 multiplied by the natural exponential squared minus 1. Okie dokie. So don't forget, don't get so excited that you found this answer. We still need to find the product of the 3. So we have pi from our theta integral. We have 2 from our phi integral. And then we have 2 times the natural exponential squared minus 1 from the rho integral. And so plugging this all in, you can say that therefore our triple integral over that solid region D of our function in terms of rho theta phi dv was equal to pi multiplied by 2 times the natural exponential squared minus 1, which leaves us with 4 pi multiplied by the natural exponential squared minus 1. And this is our beautiful final answer.